Good morning, everyone. We are a team of third year students from the Department of Electronics and Communication Engineering, Kujbiar Government Engineering College. This project, titled Development of a PID Temperature Controller using ESP32 with IoT Facility, has been carried out collaboratively by Shaharia Chaudhuri, Garima Sinha Mahapatra, Shruti Bashu Roy Chaudhuri, Arnab De, Aratrika Das, and Shushmita Gayan. Temperature regulation is essential in many fields. Our project focuses on designing a cost effective and responsive temperature control system based on a PID controller integrated with the ESP32 microcontroller. We developed this system with practical use cases in mind, such as egg incubation and lab based experiments, and enable it to work in manual, automatic, and IoT based remote control modes. Our hardware design includes the ESP32, a Wi Fi and Bluetooth enabled microcontroller which reads sensor data and outputs control signal via PWM. A DHT11 sensor which measures temperature and humidity, an AIM274 rotary encoder which helps set the target temperature manually, a MOSFET as a switching element to control the heater based on the PWM signal, a hair dryer coil as the heating element, and a fan to distribute heat evenly and maintain uniform temperature. Each of us was involved in component integration, testing, and wiring.
Here is the software implementation. Ziegler-Nicholas method is used for tuning PID constants Kp, Ki, Kd. Gain values are determined using AI for better system response. The basic PID formula is U of t is equal to Kp into E of t plus Ki into integration of E of t dt plus Kd into derivation of E of t with respect to t, where E of t is the error, that is set point minus measured temperature. The algorithm steps are: read temperature from DHT11 sensor, compute error, that is set point minus current temperature, update integral and derivative terms, compute control signal using PID formula, convert output PWM and drive heater using MOSFET, repeat at certain time interval. The proportional term reacts to the present error and its purpose is to make or give the first response. If it becomes too high, it will give too much oscillations. The integral part reacts to the past errors, that is, it will calculate the cumulated error, and its main purpose is to make the steady state error 0, and if it becomes too high, the overshoot will be too high and the system will be too slow. The derivative term reacts to the future error and it gives stability and damping. If it becomes too high, the system will be too sensitive and noisy. Here is the flowchart of the main loop. The target temperature will be set by the rotary encoder or from blink. Then the PID signal will be calculated from the current temperature and that will be sent to the blink for plot. Here is the pseudocode. All the values have been initialized here. The PID output will be mapped to 0 to 1023 to operate the MOSFET. These are the user-defined functions. The clock of rotary encoder will tell the change in state and the DT will determine the direction of rotation, and according to that the target temperature will be set. The DHT11 sensor is connected to GPIO pin 21 and the gate terminal of MOSFET is connected to the GPIO pin 2 of the ESP32. The Wi-Fi connection function will help to connect to a certain Wi-Fi network. Here is the PID control function which I have already discussed, and the blink API has two important functions, that is send data to blink, which is ESP will send data to blink, and read data from blink is the blink will send data to ESP32. And for PID configuration we have used AI to set the critical gain KU, oscillation period TU, and KP, Ki and KD.
Experimental setup and testing 1. Test bench configuration. The test setup includes a resistive heater, DHT11 sensor, rotary encoder, ESP32, and power supply. 2. Wiring diagram. The wiring diagram illustrates the electrical connections between the resistive heater, DHT11 sensor, rotary encoder, ESP32, and power supply.
So here we have the various components of our experimental setup. So first of all, we have the heating element, which is basically the main actuator that raises the temperature of the system. When the PID controller output demands heating, it turns on or modulates the power supply to the heating element. Next up, we have the fan. The fan helps as the cooling system and maintain uniform air circulation around the heated area. It can actively reduce the temperature if it overshoots the set point. Now, the ESP32 microcontroller is mainly the brain of the system. It reads the current temperature from a sensor like DTHT11, computes the PID control algorithm in real time to decide whether to increase or decrease the heating temperature. Red light indicator is actually a visual feedback to the heater when it is active. When the red light is on, it signals that the system is currently applying heat to reach or maintain the desired temperature. Blue light indicator similarly indicates that the cooling system is on, which is the fan is on or off. Push button is used to set or adjust the target temperature or set point, to start or stop the PID control process, or to switch between modes. So next up, inside the setup we have a MOSFET. It receives the high or low signal from ESP32, and also we have the sensor there. Next up, we can check our device performance. We did time domain analysis of our system. We externally plotted the temperature of the system with respect to time to check how long it's taking time. To access the control of the system remotely, we have used the Blink Cloud IoT platform. It provides real-time temperature plotting to monitor temperature. Also, it provides the control to manually set the target temperature and make the fan on or off. So in this picture, we can clearly see.
So here are the features, limitations and future work for our project. Features. We are using Ziegler-Nicholas PID tuning techniques which will improve our device performance and stability and will take less time to reach target temperature. This has manual control mode, auto mode and also remote control IoT facility. We are using one of the most efficient and cheapest microcontroller ESP32 and also using other low cost components which is eventually helping to lower the cost of the product. Limitations. We are using ESP32 rather than dedicated chips which may cause unwanted sudden errors. Our product does not have proper sealing which may cause heat leakage to the outside environment and cause delay to reach the target temperature and also cause power loss. We are using third-party IoT platform which has less reliability. It can cause connection losses and also create sudden errors in functionalities. Future work. Implementing additional control algorithms such as model predictive control MPC or fuzzy logic control FLC to compare their performance with the PID controller. Incorporating additional sensors such as humidity or pressure sensors to provide a more comprehensive understanding of the control system performance. Developing a more advanced user interface such as graphical display or mobile app to provide a more intuitive and user-friendly experience. Fabricating a dedicated microcontroller chip for this product for better performance instead of using ESP32.
We referred to several authoritative sources, including Automatic Control System by Farid Golnagri and Benjamin C. Kuo, Modern Control Engineering by Katsuhiko Ogata, the MicroPython documentation on upesi.com, and the Blink.cloud platform. We express our sincere gratitude to all our faculty members of the EC Department of Kujbia Government Engineering College for their continuous guidance and support. On behalf of our team, Shaharya, Garima, Sruti, Arnob, Arastrika, and Shushmita, thank you for your time and attention. We hope this presentation gave you a clear understanding of our PID temperature control system and inspired interest in embedded systems and automations. If you have any questions or feedback, please leave a comment below. Thank you.